So let's assume I have some sort of sequence AN, and I want to take the series of that sequence. So I want to take all those partial sums and go out. But let's say I have a problem that it's very staticky. It's got all this noise. Maybe, you know, the sequence kind of levels out, but it's nasty. You know, it's difficult to deal with. It's hard to manage. But then what if I had another sequence? I'm gonna call it BN that tracks pretty well with A sub n, and it eventually converges. And maybe another better way would be even in this case where instead of starting off, it actually is like this. You know, it starts off not looking a whole lot like A sub n, but eventually it tracks super well with it. And in that particular case, this is the essence of the limit comparison test. What it's really saying is that, look, if these sequences become really basically the same over time, then I don't have to evaluate the series for this nasty sequence. I can evaluate it for this nice clean sequence, because all we care about is the long-term behavior. Again, when you're summing up to infinity, it doesn't matter if you look at 100,000, 100 million terms, because it may be a big number, but it's not going to push off to infinity because you have something that each time you're only adding maybe a little bit. Maybe you're adding a large number, but it's still finite. Maybe big, but it's still finite. So all we really care about is that way, way long-term behavior. So as a result, if I have something that the limit as it goes to infinity comes out to be some sort of multiple, it doesn't have to be 1, because that would mean they're identical. What that means, it just has to be some sort of multiple. It means that they basically smooth out that one is a multiple of the other, so it's a scaled version of the other. If that one smoothly converges, then the other one smoothly converges, because it means they're on the same track. And again, they may not be on the same height of the track. You know, so say this one tracks exactly, but what if we had another case where it was like this? Well, in this case, they're supposed to always be positive, but the idea here is that it tracks, but it doesn't track at the same scale. It doesn't matter. You could still take the limit for, you know, if we'll call this Cn, you could still take the limit there of that sequence, or that ratio there. That's all that matters, because we're trying to say, all right, do these things basically follow the same track? And what's really nice about the limit comparison test is that if you take that limit and it comes out to be a positive, it can't come out to be 0. If it comes out to be 0, it's not helpful. It's not conclusive. But if it comes out to be a finite limit and it's positive, they either both converge or both diverge. Oh, so helpful, right? Because you can say, look, man, I don't have to evaluate this disgusting large sequence. I can just go take something simple, take the limit and say, oh, I know that converges, or I know that diverges, and you're done. So, you know, if you want a more step-by-step process, the first thing you do is you find some sort of simpler sequence. And then you just want to guarantee that, because what you're going to do a lot of times is you're going to pick a sequence that you kind of know works, right? You're going to say, look, I have to pick something that I know I can evaluate the series for. I know it's going to converge, or I know it's going to diverge. And then you want to guarantee that that limit is positive and finite, so that ratio of those things are there. And then you determine if it converges or diverges. So, you know, but a lot of times you've already done that. In this particular case, you've already picked something that you know is going to diverge or converge. Sometimes it's not that simple. You may have to use another test because you kind of narrow your problem, but you're still not quite done. It happens. And then finally, once you've done that, the answer's there. Really, the answer from here is the answer. Once you've done this third step, if this thing converges or diverges, then this thing converges or diverges. This is a really powerful tool, unlike the direct comparison test where you kind of have to like bound it and do all this stuff. You just take a limit here, you're done.